From the very first day you take creatine, something shifts inside your body long before you notice any visible change. There is no sudden surge, no dramatic transformation, no immediate strength spike in the mirror. What happens instead is biochemical, quiet, foundational. Your cells begin preparing for a different level of energy management, and that preparation matters far more than most people realize. Creatine is often marketed as a muscle supplement, a strength booster, a performance enhancer, but reducing it to those labels misses the bigger picture. Creatine is not foreign to your biology. It is a compound your body already produces and understands. It participates directly in one of the most fundamental systems that keeps you alive: cellular energy production. When you supplement with creatine, you are not introducing a stimulant. You are increasing the availability of a molecule that supports the currency of energy itself. Within the first 24 hours of supplementation, creatine begins accumulating inside muscle cells. This process is mediated by creatine transporters embedded in the cell membrane. These transporters actively pull creatine into the cell, where it becomes stored primarily as phosphocreatine. This storage form is critical because phosphocreatine acts as a rapid reserve for ATP regeneration. ATP, or adenosine triphosphate, is the molecule every cell depends on for immediate energy. Every muscle contraction, every neural impulse, every biochemical reaction that requires power depends on ATP. The problem is that ATP depletes extremely quickly. During high-intensity effort, your ATP stores can drop within seconds. Without an efficient recycling mechanism, performance collapses almost immediately. This is where creatine changes the equation. Phosphocreatine donates a phosphate group to ADP, reforming ATP at a rapid rate. This reaction happens in milliseconds. It is one of the fastest energy buffering systems in human physiology. But here is the critical insight. This process does not only matter during exercise. It matters anytime your body needs rapid energy turnover. That includes standing up quickly, reacting to sudden movement, stabilizing posture, and even sustaining cognitive focus under stress. Creatine enhances the efficiency of this system whether you are in a gym or sitting at a desk. One of the earliest physiological responses to creatine supplementation is an increase in intracellular water within muscle cells. This effect is frequently misunderstood as bloating. In reality, it reflects improved cellular hydration. Water moves into the muscle cell alongside creatine due to osmotic balance. This intracellular hydration is not cosmetic fluff. It changes the internal environment of the cell in meaningful ways. Hydrated muscle cells function differently from dehydrated ones. Cellular hydration influences protein synthesis signaling pathways, including mTOR activation, which plays a role in muscle adaptation. It improves nutrient transport efficiency and supports structural integrity of the cell membrane. In other words, that early water shift is a sign that the cell is entering a more metabolically prepared state. Inside the cell, mitochondria begin operating in a slightly different energetic context. Mitochondria are responsible for producing ATP through oxidative phosphorylation, especially during sustained activity. When phosphocreatine stores are elevated, the cell gains a more stable energy buffer. This reduces metabolic stress during repeated bouts of exertion. Instead of experiencing sharp ATP drops followed by compensatory metabolic strain, the cell maintains smoother energy turnover. Over time, this translates to improved work capacity. This is why many individuals report feeling stronger within weeks, even before significant visual changes occur. Strength gains often precede muscle hypertrophy. Performance improves first because energy management improves first. The structural changes follow later, as training adaptations accumulate under more favorable energetic conditions. Now let's shift to the brain. Your brain is one of the most energy-demanding organs in the body. Although it represents only a small percentage of total body weight, it consumes a disproportionate share of resting energy. Neurons require constant ATP availability to maintain ion gradients, fire action potentials, and reset after signaling events. Energy instability in the brain contributes to cognitive fatigue, slower reaction times, and reduced mental endurance. Creatine crosses the blood-brain barrier and increases brain phosphocreatine stores over time. This does not produce a stimulant-like effect. There is no caffeine-style alertness spike. Instead, what occurs is improved energetic resilience. When neurons have faster access to ATP regeneration, they recover more efficiently between firing cycles. This supports working memory, reaction speed, and resistance to mental fatigue, particularly under conditions of sleep deprivation or high cognitive load. Research consistently shows that creatine supplementation can improve cognitive performance in individuals exposed to demanding mental tasks. Interestingly, vegetarians and vegans often demonstrate more pronounced improvements, likely because their baseline creatine intake from dietary sources is lower. This highlights that creatine's role extends beyond athletics. It supports cellular energy dynamics in multiple organ systems. Returning to skeletal muscle, another key adaptation involves glycogen utilization. During high-intensity activity, the body relies heavily on glycogen breakdown. However, when phosphocreatine availability increases, immediate ATP demand is partially buffered by the creatine system. This can spare glycogen during short bursts of explosive effort. Over repeated sessions, this improved energy partitioning contributes to enhanced training capacity. Creatine also reduces the accumulation of certain fatigue-associated byproducts during intense effort. When ATP turnover is more efficient, there is less reliance on rapid glycolysis in the earliest seconds of activity. This can modestly influence acid accumulation inside muscle fibers, making repeated high-power efforts more sustainable. While creatine is not an endurance supplement in the traditional sense, it enhances the quality of repeated high-intensity output. Recovery is another area where creatine demonstrates measurable benefits. After training, muscle fibers must restore ATP, repair contractile proteins, stabilize membranes, and manage inflammatory signaling. All of these processes require energy. Faster ATP regeneration supports these repair mechanisms. Additionally, improved intracellular hydration may facilitate nutrient delivery and structural restoration. Importantly, decades of research show that creatine supplementation at recommended doses is safe for healthy individuals. Concerns about kidney damage largely stem from confusion between creatinine and kidney pathology. Creatinine is a normal byproduct of creatine metabolism. Mild elevations in blood creatinine during supplementation do not indicate renal damage in individuals with normal kidney function. Large-scale reviews consistently support creatine's safety profile when used responsibly. So what truly happens when you take creatine daily? Your body does not suddenly become larger or dramatically transformed. Instead, it becomes more energetically prepared. Cells gain faster ATP recycling. Muscles gain improved hydration and buffering capacity. The brain gains greater resistance to cognitive fatigue. Over time, these subtle shifts compound. Performance improves, recovery stabilizes, and the foundation of cellular energy becomes more robust. And this is only the beginning. As creatine supplementation continues beyond the first few days, the body transitions from acute adjustment to structural adaptation. Around the second and third week, muscle creatine stores approach saturation. This is when the biochemical groundwork laid during the first phase begins translating into measurable performance differences. The change is not explosive, it is cumulative. Energy turnover becomes more reliable. Neuromuscular coordination sharpens. Repeated high-intensity efforts feel less draining. One of the most significant adaptations during this stage involves the nervous system. Strength is not purely a property of muscle size, it is also a property of neural efficiency. When ATP availability improves within muscle fibers, the nervous system can recruit motor units more effectively. Motor unit recruitment determines how many muscle fibers activate during a contraction. Enhanced recruitment increases force output even before hypertrophy occurs. This is why many individuals experience strength gains within weeks, despite minimal visible changes in muscle mass. At the cellular level, elevated phosphocreatine stabilizes energy supply during repeated contractions. This reduces the metabolic crash that typically follows intense effort. Instead of oscillating between high output and rapid fatigue, the muscle sustains more consistent power. Over multiple training sessions, this consistency amplifies adaptation. Muscles exposed to higher quality training stimuli respond by reinforcing contractile proteins, strengthening connective structures, and improving resilience. Another underappreciated adaptation occurs in relation to muscle damage and inflammation. High-intensity exercise inevitably produces microtrauma in muscle fibers. This damage is necessary for growth, but must be managed efficiently. Creatine appears to modulate certain inflammatory markers and support membrane integrity, allowing muscle cells to recover with less prolonged disruption. Recovery does not become effortless, but it becomes more predictable. Training sessions begin to build on each other rather than being interrupted by lingering fatigue. Now consider glycogen dynamics more closely. Glycogen serves as the primary fuel for sustained high-intensity effort. When phosphocreatine provides rapid ATP buffering in the initial seconds of activity, glycogen breakdown can be slightly delayed. Over time, this contributes to improved energy partitioning. The muscle learns to deploy energy systems more strategically. While creatine is not a direct endurance enhancer, it improves the efficiency of transitions between immediate and glycolytic energy pathways. This subtle optimization often manifests as improved performance in interval training, sprint cycles, and repeated power movements. Hormonal interactions also deserve attention. Creatine does not function as a hormone, but it indirectly influences the hormonal environment by enhancing training quality. When individuals train at higher intensities due to improved ATP availability, the body generates stronger anabolic signals. Mechanical tension and metabolic stress are primary drivers of muscle adaptation. By allowing more sustained high-intensity effort, creatine amplifies these signals without artificially manipulating endocrine pathways. There is also evidence suggesting that creatine may influence satellite cell activity. Satellite cells are involved in muscle repair and growth, contributing nuclei to muscle fibers during adaptation. Some research indicates that creatine supplementation, combined with resistance training, may enhance satellite cell proliferation. This does not mean creatine independently builds muscle without stimulus. It means that in the presence of training, creatine may create a more favorable cellular environment for structural growth. Beyond muscle and strength, long-term creatine supplementation reveals broader implications for aging. Muscle mass naturally declines with age in a process known as sarcopenia. Reduced muscle mass correlates with decreased mobility, metabolic dysfunction, and loss of independence. Because creatine supports ATP regeneration and muscle quality, it has been studied extensively in older populations. Results consistently show improved strength, functional capacity, and preservation of lean mass when combined with resistance training. This is not merely about aesthetics. Muscle tissue acts as a metabolic reservoir. It contributes to glucose disposal and insulin sensitivity. Improved muscle function can enhance metabolic stability, especially in individuals with sedentary lifestyles. While creatine is not a treatment for metabolic disease, its role in supporting muscle energetics indirectly contributes to healthier glucose handling during physical activity. The brain adaptations discussed earlier also deepen over time. As brain creatine stores gradually saturate, cognitive resilience becomes more stable. Individuals exposed to chronic stress, demanding workloads, or irregular sleep patterns may experience sustained improvements in mental endurance. Rather than producing heightened stimulation, creatine supports the brain's ability to maintain steady performance under strain. This distinction is important. It enhances capacity without overriding natural regulatory systems. Safety remains one of the most extensively studied aspects of creatine. Long-term trials spanning years have demonstrated no harmful effects in healthy individuals using standard dosing protocols. The body regulates creatine saturation naturally. Once muscle stores are full, excess creatine is converted to creatinine and excreted. This self-limiting mechanism contributes to its safety profile. Concerns often arise from misunderstanding laboratory values rather than documented pathology. Dosing strategies also influence adaptation timelines. A loading phase of approximately 20 grams per day for 5 to 7 days can accelerate saturation. However, consistent daily intake of 3 to 5 grams without loading eventually achieves similar muscle creatine levels over several weeks. The slower approach minimizes gastrointestinal discomfort for sensitive individuals. Both strategies ultimately converge in outcome. Elevated phosphocreatine availability. Hydration remains important during supplementation. Because creatine increases intracellular water, adequate fluid intake supports overall balance. Contrary to outdated myths, creatine does not increase dehydration risk when proper hydration practices are followed. In fact, improved cellular hydration may support thermoregulation during intense exercise. At this stage, several weeks into daily use, the cumulative effects become clearer. Strength improvements stabilize, recovery shortens, mental fatigue decreases under demanding conditions. None of these changes are dramatic in isolation. Their power lies in consistency. Each training session benefits from slightly better energy turnover. Each workday unfolds with slightly greater cognitive stability. Over months, these marginal gains compound into meaningful difference. And this leads to an important realization. Creatine is not about forcing adaptation, it is about removing energetic bottlenecks. When ATP recycling becomes more efficient, biological systems operate closer to their inherent potential. Muscle, brain, and metabolic pathways all rely on energy currency. By strengthening that currency's recycling system, creatine reinforces the foundation on which performance, resilience, and long-term health are built. But there are still critical misconceptions to address and deeper physiological nuances that most discussions overlook. Despite being one of the most researched supplements in modern nutrition science, creatine remains surrounded by persistent myths. These misconceptions often overshadow decades of controlled clinical data. To understand creatine fully, it is essential to separate physiological reality from assumption. The most common concern involves kidney health. The confusion largely stems from creatinine, a metabolic byproduct of creatine breakdown. When someone supplements with creatine, blood creatinine levels may rise slightly. However, creatinine is routinely used as a marker of kidney filtration. This overlap has led many to incorrectly assume that increased creatinine automatically signals kidney stress. In healthy individuals with normal renal function, controlled trials consistently show no evidence of kidney damage from recommended creatine dosing. Long-term studies, including those lasting several years, confirm stable renal markers when creatine is used responsibly. The distinction is critical. Elevated creatinine during supplementation reflects increased creatine turnover, not impaired kidney filtration. Another widespread myth is that creatine causes dehydration or muscle cramping. This belief likely originated from early anecdotal reports among athletes training in hot climates. However, controlled research does not support this claim. Creatine increases intracellular water within muscle cells, not extracellular fluid under the skin. This shift enhances cellular hydration rather than depleting it. Several studies actually demonstrate reduced incidence of heat-related illness and muscle cramping in athletes using creatine compared to placebo groups. Adequate fluid intake remains important, but creatine itself does not inherently cause dehydration. Concerns about hair loss also circulate frequently. This idea is based on a small study suggesting that creatine supplementation might increase levels of dihydrotestosterone, DHT, a hormone associated with male pattern baldness. However, the evidence remains limited and inconsistent. The study in question did not directly measure hair loss and involved a small sample size. Subsequent research has not conclusively replicated significant DHT elevations. At present, there is insufficient evidence to conclude that creatine causes hair loss in healthy individuals. Behavioral myths also persist. Creatine is sometimes mistakenly grouped with anabolic steroids or stimulants, leading to assumptions about aggression or mood instability. Creatine does not act on androgen receptors and does not artificially elevate testosterone beyond normal physiological range. Its mechanism is purely energetic. In fact, some research suggests potential mood-supportive effects due to improved cellular energy metabolism in the brain. By stabilizing ATP availability, creatine may support neural resilience rather than disrupt it. Now, let's explore deeper neurological implications. The brain relies on constant energy turnover to maintain synaptic transmission. Under conditions of metabolic stress, such as sleep deprivation, traumatic brain injury, or neurodegenerative disease, ATP depletion becomes a limiting factor. Creatine's ability to enhance phosphocreatine stores in neural tissue has led researchers to investigate its role in neurological support. While it is not a treatment or cure, studies have explored creatine in contexts such as mild traumatic brain injury, Parkinson's disease, and depression. Results vary, but the consistent theme is this: improving cellular energy availability may offer protective advantages in energy-compromised states. Sleep deprivation provides a clear example. When individuals are deprived of sleep, cognitive performance declines partly due to impaired energy regulation in the prefrontal cortex. Research indicates that creatine supplementation may mitigate some aspects of cognitive decline during short-term sleep loss. Reaction time and working memory appear more stable in supplemented individuals. This reinforces the concept that creatine enhances energetic buffering rather than stimulating alertness artificially. Another emerging area of research involves metabolic stress and mitochondrial health. Mitochondria generate ATP through oxidative phosphorylation, but this process can become inefficient under chronic stress. By supporting rapid ATP recycling, creatine reduces pressure on mitochondrial pathways during high-demand periods. This does not replace mitochondrial function. It complements it by smoothing energy transitions. Over time, this energetic stability may reduce cumulative cellular strain. Who then should consider creatine? Athletes engaged in high-intensity or resistance training stand to benefit most clearly. However, older adults aiming to preserve muscle mass and functional strength may also gain significant advantages. Individuals with high cognitive workloads, such as students or professionals under chronic stress, may experience improved mental endurance. Vegetarians and vegans, who typically consume less dietary creatine, often demonstrate pronounced responses. Who should approach with caution? Individuals with pre-existing kidney disease should consult healthcare professionals before supplementation. While evidence supports safety in healthy populations, compromised renal function requires individualized assessment. Pregnant or breastfeeding individuals should also seek medical guidance due to limited long-term data in those populations. Dosing remains straightforward. A loading phase accelerates saturation but is not mandatory. Consistency matters more than speed. 3 to 5 grams daily is sufficient for most adults. Timing relative to workouts appears less critical than once believed, although some evidence suggests post-exercise ingestion with carbohydrates may enhance uptake due to insulin-mediated transport. Ultimately, total daily intake over time determines saturation. At its core, creatine supplementation represents an enhancement of an existing biological system. It does not override physiology. It supports it. By strengthening ATP recycling, creatine reinforces the energetic foundation upon which muscle contraction, neural signaling, and metabolic regulation depend. This is why its effects feel subtle yet powerful. There is no dramatic spike. There is no hormonal surge. There is only improved readiness. Cells respond faster. Recovery stabilizes. Energy dips become less disruptive. Over weeks and months, these marginal improvements accumulate. The true value of creatine lies not in spectacle, but in stability, not in sudden transformation, but in sustained capacity. It is one of the rare supplements where scientific consensus, safety data, and real-world application converge. And when a molecule can consistently strengthen the fundamental currency of life, ATP, it does not need hype. It needs understanding. Creatine is often misunderstood because its effects are not dramatic in the short term. It does not stimulate your nervous system. It does not artificially elevate hormones. It does not override your biology. Instead, it strengthens one of the most fundamental systems your body depends on, ATP recycling. Every contraction, every thought, every adaptive response begins with energy availability. When ATP regeneration becomes more efficient, performance does not spike, it stabilizes. Strength improves not because muscle suddenly changes, but because energy management improves first. Recovery becomes more reliable because repair processes have the fuel they require. Cognitive endurance increases not through stimulation, but through enhanced energetic buffering in neural tissue. Over weeks and months, these subtle improvements compound. Training sessions become more productive, fatigue becomes less disruptive, mental performance under stress becomes more resilient. The real value of creatine lies in its consistency. It reduces energetic bottlenecks and allows your physiology to operate closer to its inherent capacity. Decades of research support its safety in healthy individuals when used at recommended doses. Unlike trend-driven supplements built on bold claims and limited evidence, creatine's reputation rests on controlled trials, long-term data, and reproducible outcomes. It is not a shortcut. It is not a transformation in a bottle. It is a foundational support system for cellular energy. When you strengthen the currency of life, ATP, you do not force change, you enable it. And that is why creatine remains one of the most reliable, evidence-based tools in performance and health science today.